Okay, so today's lecture will be on the global climate and environmental change. So this was a part of the course where we're basically going to go through describing how the Earth's climate works. That fits in a little bit to the history of life part of the course, which Steve has been doing in terms of how the planet has been habitable. So rather than looking at the life itself, we're going to be looking at the climate system part of the Earth. So there's some suggested reading here. I think this textbook at the top, The Earth's Past, Climate and Future, is available in the library. It's what quite a lot of the lecture material is kind of loosely based on. I don't think it's available in print at the moment, or it is, and it's extremely expensive. So don't feel you have to get that book, okay? This one at the bottom is quite good as well. Atmospheric change. But I guess the thing I want to point out is that you don't really need to read all of those textbooks. I've put as much material on Learn and kind of in terms of electronic resources, which should help you kind of learn the content. Okay? Okay, so hopefully some of you, well, 19 views of modeling the Earth's climate. So I'm just going to whiz through this quite quickly. So this is the idea that the Earth, at the bottom here, it's the temperature of the Earth is basically dependent on all of these fluxes up here. So we've got, let's see if I just give myself a little pointer, laser pointer. Okay, so we've got energy coming in from the sun, okay, and some of that is reflected away by clouds and whatnot. Okay, some of it gets to the Earth's surface and is reflected away. That's what heats up the Earth. And then that energy then is re-radiated back out to space because the Earth has a temperature, and anything object that has a temperature will radiate heat away. Now, in the simple case, which we went through in the introductory video, we just considered these yellow fluxes. Okay, so we didn't consider that the Earth had an atmosphere, and that's what we're going to go through today. But the atmosphere does have a role to play here because it stops some of that energy radiating directly back out to space. And we'll see how that affects the climate. So just briefly, so this is kind of this concept of the black body. So any object that has any temperature above absolute zero, so above minus 273.15 degrees Celsius, 0 Kelvin, will radiate energy away from it. So the colder it is, the less energy it will radiate away. So hot objects radiate a lot of energy, and they tend to radiate it at shorter wavelengths, so white-coloured light from the sun because it's very, very hot. Whereas cooler objects, so like us, that's a horrible pun, so we give out less energy than the sun, okay, and we give it out at a longer wavelength. So we're giving out energy at the infrared wavelength, okay? And this is the equation that basically describes that. So this thing down here, so the amount of energy emitted per square meter of an object is equal to the Stefan-Boltzmann constant, okay, times temperature raised to the power 4. So a small increase in temperature leads to a big increase in energy being radiated away. So this is the sun, this is the Earth, quite obviously. So the further you are away from something, the more dilute that energy will be from the sun. So imagine, so the total power of the sun, kind of Q in this equation down here, the further you get away, that energy is, imagine that spread out over a sphere that's got a radius of however far you are away from the Earth. Okay, so this is where this R in this equation here comes from. So that's the distance between the Earth and the sun. So when the solar basically radiation gets to the Earth, if you basically put up a big 1 meter square and pointed it at the sun in space, you'd get 1,367 watts of energy coming into that square meter. But it's not quite that simple because the Earth is round. Okay, so the amount of energy that the Earth receives is equal to that amount per square meter times the area of the Earth's shadow. That's basically how much energy that the Earth blocks out from the sun. So that's this part on the top here, so the solar flux times the area. But that energy is not just hitting one side of the sun, okay? It's spread out over the whole Earth as the Earth rotates around. So it's actually spread out over the surface area of the sphere. Okay, so that's where the 4 pi a squared. So in this case, a is the radius of the Earth for no particular reason, just we need another variable than r. So this equation simplifies to S0 divided by 4. So every square metre of the Earth, on average, gets 341 watts per square metre. Okay? So that's this number coming in at the top. This is basically how much energy is arriving at the top of the atmosphere of the Earth. Some of that is reflected. Okay? So it's reflected by clouds, because they're kind of white coloured. So light just kind of reflects off those. Some of it's reflected by the surface. So these are kind of some images of parts of the Earth, and you can see that different parts of the Earth have got different reflectivities. So something like an ice sheet, that's quite white, that might reflect a lot of energy from the sun, whereas an area like a forest, okay, that's got lots of dark trees, that might absorb more energy than it reflects. So this is kind of the situation. We've got some energy coming in, and then some is reflected out to space directly. Okay, and then that leaves some other amount that is absorbed by the Earth that's not reflected out. Okay, and that causes the Earth to heat up. It gets hotter and hotter and hotter, and the hotter it gets, the more energy it radiates away. Okay, because of that Stefan-Boltzmann relationship, which means at some point the energy in must equal the energy out. So the Earth heats up until it can radiate heat away fast enough that it's receiving from the sun. So this is the basis of the model that we went through in the introductory video. So the incoming shortwave radiation is just the solar constant divided by 4. So that's the 341 watts per square metre. The amount reflected is the amount received, S0 divided by 4, times the reflectivity. Okay, so if the Earth is a perfect reflector, if it's like a mirror, then alpha would be 1. So it would reflect away all of the heat energy that arrives, and it would stay cold. If the Earth was a perfect black body, in that it absorbed all of the energy it received, then alpha would be 0, and we wouldn't reflect away any energy. Okay? So the total amount absorbed is the total arrived, okay, minus the amount that's reflected. So that's that equation down at the bottom. So we can then, we've got these two terms now. This is the amount absorbed, which is the coming in minus the going out in terms of the shortwave radiation. And then the Earth heats up, okay, and then radiates away dependent on that sigma temperature of the Earth raised to the power of 4. Okay? So we can just quite easily just say that those two things, if they are equal to each other, so the temperature of the Earth is not increasing or decreasing, if we're in steady state, that is the equation we get, and we can rearrange that equation to get a temperature for the Earth. Now this TE, okay, this actually refers to the emission, it's what we call the emission temperature. So it's not actually the temperature of the Earth because this hasn't yet got an atmosphere in it. So this is kind of like the temperature of the top of the atmosphere. If we consider the Earth as like a whole system, then all of these things have to be true. Okay, so the amount reflected from the atmosphere and the surface of the Earth must equal the total energy that's being emitted by the whole Earth and the atmosphere. So we get this equation here, and this allows us to do some, go on basically to say so that the reflectiveness, sometimes referred to the albedo, is the fraction of solar energy that comes in that is reflected, and you can see from this map of albedo that it's not constant over the whole Earth. So for instance, the oceans have got quite a low albedo because they're kind of blue coloured and they absorb a lot of light made of water. Large parts of the continents also have quite low albedo, particularly things that have got lots of trees on. They absorb lots of incoming radiation. But regions that don't have lots of trees on, like for instance desert regions, okay, they tend to reflect a lot of light, so they have a different albedo. Polar regions where there's lots of ice also reflect a lot of light. So the average value is about 0.3, averaged over the whole Earth. Okay, so it's not the same everywhere, but it's kind of approximately 0.3. So we can plug numbers that we know into this equation. Okay, so we know the solar constant, we know alpha, we know the emissivity, that's 0.3. We know the Stefan-Boltzmann constant, which is that thing down there. We can plug those numbers in and get an answer of 255 Kelvin, okay, which is minus 18 degrees Celsius. Okay, so that's approximately the temperature of the Earth, kind of to the nearest 50 degrees Celsius. Okay, so we know that the Earth isn't that cold, okay, because the Earth isn't mostly frozen. Okay, so there must be something else that's causing the Earth to be a bit warmer than this, and this is the greenhouse effect, which probably we'll become more familiar with now. But we're at least within the right ballpark here, if though too low temperature. So the temperature actually, average temperature is more like 15 degrees. So there's some amount of extra warming caused by us ignoring or not having in our model this atmosphere. So we're going to go and do that now. So this is where the stuff starts in your handouts. So the incoming radiation from the sun is in red here. So the intensity on the vertical axis up there at the top, and then the wavelength along the horizontal axis. So short wavelength, but high intensity. And if you look at the temperature of the Earth is colder, so it's giving out much longer energy radiation. And now if you look at what happens as this stuff goes to the atmosphere. So there are a bunch of different gases in the atmosphere: water, carbon dioxide, nitrous oxide, all these methane kind of stuff like that. And they absorb light at different wavelengths. Okay? And you can see that some of these are quite specific. So for instance, carbon dioxide, there's a lot of absorption here, but not in this spectrum over here. So if you add up all the absorbance of all of the gases in the atmosphere, you kind of get this graph in the middle here. So you can see very, very short wavelengths, the atmosphere is totally opaque. It absorbs all of the light coming in on it. But that's okay because there's not a lot of light in that spectrum up there. It's quite good as well because that's the really highly energetic light, the UV light that's coming from the sun. Almost all of that is blocked, which is good because that means that we don't get cancer. Likewise, almost all of the very, very long wavelength light, that's also blocked. But there are these windows where basically light can get through, and that happens to be at the visible spectrum, okay, which is quite fortunate because our eyes evolved to see that light. So we've got this term absorptivity or emissivity. Okay, so these are actually the same thing, and they're basically the fraction of a black body that thing is. So in this case, we're referring to the atmosphere. So at this wavelength here, okay, it would be an almost perfect black body. The emissivity or absorptivity would be 1. Whereas in this bit of the spectrum here, the absorptivity would be very, very low. Okay? If you look at the bit of the spectrum which refers to the approximate temperature of the Earth's radiation, okay, we can see that we have this window in here where the emissivity is low, but for most of the window, the emissivity is high. So we're basically, the absorptivity, we're really absorbing a lot of that incoming radiation or outgoing radiation, so the stuff that's coming from the Earth and is radiating back out to space. A lot of it gets blocked by the atmosphere. So absorptivity is wavelength dependent, okay? And the way that it's used in climate science, it's almost always just used to refer to the average over the window where the Earth's temperature is important. Okay, so the infrared wavelengths. So that gives us something to add into our model. So we've got this, the red lines on here of what we've already discussed. So this is the incoming solar radiation, comes into the surface and then is reflected away. And this albedo here refers to the reflection at the surface and in the atmosphere. But then that causes the surface to heat up, and that radiates off out into space. But this time, we've got the temperature of the surface radiating out into space, and that doesn't all get out. So some of it it's basically the total amount emitted at the surface minus the amount which is absorbed by the atmosphere, by the absorptivity. Greek eta there. So that's blocking radiation going out. That causes the atmosphere to absorb some of that radiation. So that means that the atmosphere must have a temperature, okay? And that means the atmosphere must have a temperature, and it will therefore be radiating stuff out into space again, okay? And that will be equal to the Boltzmann constant times the temperature to the power 4. But because the atmosphere isn't a perfect black body, okay, we've got this emissivity constant here, which is broadly the same as the emissivity. So that's why we've given them the same symbol. Okay, and that's because the temperature of the atmosphere and the surface are similar enough that we can consider they're effectively acting at the same wavelength. So what we do now, okay, so that's explained those things there, is we basically think about, can we now do a same kind of balance as we did for the simple model by just looking at the top of the atmosphere and at the bottom of the atmosphere, can we balance all of the fluxes of radiation? Okay, so at the top of the atmosphere, we're looking at the downwards flux of energy equaling the top upwards flux of energy, and at the bottom of the atmosphere doing the same thing. Okay, so at the top of the atmosphere, the downwards flux is essentially this term, okay, because we've got the incoming minus the outgoing, and that is equal to this term here. So we're just balancing those in and out terms. Okay? We can do the same thing at the ground, okay, because this is now the same here, except we've got this other term of stuff going out here, okay, and stuff, well, this is, yeah, stuff going in, stuff going out there. So that gives us two equations, okay, where we know everything except the surface temperature and the atmospheric temperature. And this is the maths that you can go through to take those two simultaneous equations and solve them. So the first thing you do is you rearrange each of the equations to make the temperature of the atmosphere, basically the subject, or eta Boltzmann constant times the temperature of the atmosphere to the power 4 equal. So that means you can then combine those two equations into one equation, and then you start to rearrange that, and how to rearrange that is on there. You've got it in your notes. And ultimately, that then gives you this equation at the bottom, okay, which allows you to work out the surface temperature, which is a function of the solar constant, so the power of the sun, so that the hotter the sun gets, the more energy the sun gives out, the warmer the surface of the Earth gets. It's got a term of the albedo in here, so the more reflective the planet is. Okay, so the bigger this number is, the smaller this number is, which means that more reflective planets are cooler. And we've got this term emissivity in here. So the more absorptive or emissive the atmosphere is, the warmer the planet will get. Okay, so this is a very important equation. Okay, so we'll be using this equation throughout the next couple of lectures to see how changing the environment affects all of these parameters and how that affects the temperature of the Earth. Okay, so you can also show that there is a relationship between the temperature of the atmosphere and the temperature of the surface, if you so choose. So we can go through and do the same kind of plug and chug with the numbers. So we've still got the the albedo of 0.3, emissivity of 0.8. So that's the kind of the basically fraction of this outgoing radiation that is absorbed by the atmosphere. And we do that, and you can do that as you want to, and that will give you a temperature of 288 Kelvin, which is much closer to the real temperature of the Earth. So just with this very simple model that's only got one layer of atmosphere, that assumes that the albedo is the same everywhere over the planet, that the emissivity is the same as the absorptivity, wavelength specific, and all that kind of stuff. It performs very well in getting the absolute temperature of the Earth compared to, you know, enormous climate models that run on huge supercomputers over many, many hours of computing time. With just a pen and a piece of paper, you can kind of work out the temperature of the Earth. So this is kind of the stuff you kind of like should know. So the surface temperature, atmospheric temperature can be kind of calculated from those kind of equations. The emission temperature is the kind of the temperature the planet would be if it didn't have an atmosphere at all. So if someone blew away all the atmosphere, then that would be the temperature of the Earth, which is colder than the surface temperature if we do have an atmosphere. It's also the temperature of the top of the atmosphere. So if you were in space and you were looking down at Earth and you measured the wavelengths of light coming off Earth and you went, right, well, that suggests from the wavelength of light what the temperature is using the Stefan-Boltzmann and the Wien's law, which went through in the introductory video, that would be what the Earth would look like. Okay, so it's kind of like the top of the atmosphere temperature. So we've got the solar constant, the albedo, emissivity or absorptivity, and Stefan-Boltzmann constant. And you can kind of go back through the lecture and fill out what units those should be in as well. That would be helpful. So another video which I asked you to watch was the Minute Earth video on the faint young sun paradox. So for those of you that didn't watch that, basically astrophysicists that basically calculate and basically investigate how stars evolve, they figured out that in the early kind of when the solar system was younger, the sun was not as powerful as it is now because it was burning, it hadn't produced as much helium, so it was kind of a little bit less dense, lower temperatures. So the power of the sun, so this is at the top we've got basically now, and this is basically 5 billion years ago at the bottom of the graph. The sun was a lot less powerful than it is now. Okay, so that should mean that using that equation at the top, if we make the sun less powerful, the surface temperature should be much colder. Yeah? If S0 is smaller, then TS should be smaller. So it turns out that means that if you use the current albedo and emissivity, you get a much, much, much colder temperature. Much colder. So cold, in fact, that all of the oceans would be completely frozen and would be locked into this kind of very, very high albedo state. If all the oceans were frozen, they'd be white, they reflect light out into space, and the planet would be locked forever in this kind of very, very, very cold state. Now, one of the ways around that problem is that, as explained in the video, that in the early Earth it's thought that we had much more and perhaps different greenhouse gases that kept this temperature here, so the emissivity would have been much higher. Therefore, the temperature of the Earth could have been compensatedly higher for the lower sun output. Okay, so we've been through and described two models of the Earth in terms of their temperature, one with an atmosphere, one without. And looking at those models, we can then see how the reflectivity of the Earth and the Earth's atmospheric composition can control temperature, as well as the sun's output. So we're going to go on now to talk about a little bit about the climate system and introduce some of the features of that before we then go on next lecture to look at how the climate has perhaps changed through geological time, through changing some of those terms in that equation. So just some terms that are will become important. So climate forcing, so that's something that happens in the Earth system that changes the climate. Okay? That is independent of the climate itself. Okay, so that could be changing the power of the sun over time, okay, because that's not dependent on anything in the Earth system. It could be volcanoes going off and giving out climate-relevant gases, okay, because whether a volcano goes off or not is mostly not relevant, is mostly not determined by the climate. The climate response is how much the climate changes to those forcings. And that can be in terms of a temperature change, a precipitation change, a sea level change. The sensitivity, climate sensitivity, is basically the magnitude of that response per forcing. So if you double CO2, what's the change in temperature? The response time is the time it takes for that change to happen. So some changes are almost instantaneous. So if you double the power of the sun, it's going to get warmer almost instantly. Okay? But if you increase the greenhouse gas concentration, that might have other impacts on the climate system, maybe on changing the biosphere, which then has another effect, which takes a long time to propagate through until you get to a stable state. So the climate response time can be very, very short, but there are things that can change in the climate system which will take many millions of years, and we'll go through some examples of those in the next lecture. And then the other thing, which we'll come to again and again and again, is this thing called climate feedbacks. So this is something that changes the Earth's climate, say for instance temperature, but is driven by an initial change in temperature. Okay, so this is, so for instance, if it gets warmer, okay, that means that we are going to be able to dissolve less carbon dioxide in the ocean, because gases find it harder to dissolve in liquids when it's hot. Okay? So that will then cause there to be less carbon dioxide in the ocean and more in the atmosphere, which will make it warmer, which will then make the less carbon dioxide dissolved in the ocean, more in the atmosphere, which will then make it warmer. And you get this constant feedback loop of one change causing, like in the climate, causing a change in one of the parameters that controls climate, albedo or emissivity. And then that goes round and round and round, amplifying the change. There are feedbacks which are negative, okay, which make the change less. So if you make the climate warmer, that might change the amount of weathering you get, and we'll see next lecture the effect of weathering is actually to reduce the temperature of the Earth. Okay? So these feedbacks are really important in determining the climate response time, so how fast climate changes to a given change in forcings. So what is climate? So the equation that I've shown so far has got a single temperature. Okay, temperature equals something. Okay, which I'll let you guys remember. But the Earth isn't just one temperature. So a description of the Earth's climate is not just its average temperature, but it's also the temperature distribution. So maybe the gradient of temperature from the equator to the poles. You could also include things like the seasonality in temperature. So how much winter is colder than summer. So that's part of the description of climate. So climate is not just kind of one number average temperature. Okay? So there's a nice GIF there. Yeah. So I guess also climate is also not just temperature. It's all things like precipitation, things like that, storminess, variability in storminess. All that things fits into the description of what is climate. Okay. So just a little bit of descriptions about parts of the climate system now. So the atmosphere is kind of can be described as having a number of layers. So there's the troposphere, which is the bit nearest the ground. That's where most of the mass of the atmosphere is. As you go further and further up, the density of the atmosphere gets lower and lower and lower. But if you think about how the atmosphere is heated up, okay, from that simple model, the atmosphere is actually not heated much from the sun coming in at the top. It's heated from the energy that's radiated from the Earth. So the atmosphere is heated from the bottom. Okay, so the atmosphere is heated because the Earth is warm. Solar radiation just shines straight through it. There's a little bit of absorption in the stratosphere, okay, by molecules like ozone. So that means that the atmosphere gets heated up here and it gets heated down here. And this is important because if you heat something at the bottom, okay, it gets less dense and rises up. Okay, which means that this part of the atmosphere is really, really well mixed. Whereas the stratosphere at the top here, that's heated from up here, so it means that this air is almost always warmer than the air down here, which means that it's not very well mixed. It's very hard to mix that vertically. Okay, so it's why it's called the stratosphere, because it's stratified. It's very well layered. It's very hard to mix, whereas the troposphere is very, very well mixed. That's the composition of the atmosphere. I don't think you do not need to know that. I mean, the atmosphere is mostly nitrogen and oxygen, lots of water vapor. some trace gases. Most important one is CO2. We'll come on to those when they're important. Don't bother learning that now. So the simple equation for the kind of the temperature of the Earth, that doesn't take into account the fact that at the equator, okay, we get more energy arriving per square meter because at the poles the sun is basically spread out over, sunlight is spread out over a wider area. So that means that if we look at the amount of energy that's absorbed, okay, so we get much more energy absorbed by the Earth at the equator, whereas less at the poles. And if you've ever been to the equator, you'll notice it's quite hot compared to where we are in Scotland. And that's because it's pointing more towards the sun than we are. That leads to there being a difference in the outgoing radiation as well. So because the region around the equator is warmer, then it gives out more heat back out to space than the polar regions because of that Boltzmann constant T to the power of 4 relationship. So you can see over the actual equator there's a little bit of a low, and that's because there's lots of clouds over the equator because of the intertropical convergence zone. It rains a lot there, and those clouds stop that radiation getting out to space. But largely we have this pole temperature gradient in terms of incoming radiation and outgoing radiation. But if you take one away from the other and look at the net effect, okay, they don't balance out. So although the tropics are radiating more heat out to space, they're not radiating out as much as they receive. Okay, so that means that there's a net gain of energy in the equator and a net loss at the poles. And that can't be sustainable, because if that were sustainable, then the poles would just get colder and colder and colder and colder. So to maintain this kind of surplus of energy coming in at the equator and this deficit at the poles, the atmosphere has got to move that heat, okay, from the equator to the poles. And this is what drives our atmospheric circulation. It's why we get weather. So the equator is warm, that causes air to rise up. Okay, that is this kind of Hadley cell circulation, which transports heat from the equator ultimately to the poles. Okay. So this is slightly modified by the fact that the Earth rotates. So the air doesn't move directly from the equator to the poles. It's offset by the Coriolis force, which if you do the oceanography course next term or next year, you'll learn more about the dynamics of that. Or if you do atmospheric, what's it called? Atmosphere, something. The meteorology courses, there are 2 of them. They're really good. They'll tell you all about that. So this is basically what we end up with, because it's not just as simple as the Coriolis force. We have also land masses in the way that deflect the air currents. So if we think about the ocean now, so the ocean is similar to the atmosphere, so it's a fluid. It moves around. It's heated by the sun. And it's also heated by the atmosphere. So the atmosphere also radiates energy back down to the surface of the ocean. And it moves around because it's on a rotating sphere. So things like the Coriolis effect, they still affect its movement. But unlike the atmosphere, so the atmosphere is fairly continuous around the globe. Okay, there's nowhere you go and there's no atmosphere. Whereas the ocean, it's split up into a number of separate basins, like the Atlantic Ocean, the Pacific Ocean. And even within those basins, you can see that the topography is actually quite extreme. So if you look at a map like that, it looks a little bit like the ocean floor is actually quite smooth and kind of uninteresting, but actually it's not. You get a lot more topography in the ocean than it gets credit for. And that has a really big control on where it can circulate. It's also heated from the top. Okay, so don't do this experiment, but if you get a pan of water and you put it on a stove and you heat it from the bottom, okay, it will boil, okay? And it will boil because the water can convect up, round and round and round, and heat up the whole thing of water, and it will eventually get to 100 degrees Celsius and boil. Whereas if you put it under the grill, Okay? If you try and put water under the grill, it will never boil. Okay? Because all that happens is the surface layer of water heats up. Okay? And because warm water is less dense than cold water, that layer of warm water stays at the top and evaporates. I mean, it does get to 100 degrees C, it evaporates. But then, but that evaporation cools down the water underneath it. And the level of water will go down and down and down and down until you get a tiny drop at the bottom. And maybe that will boil as it's heated up from the pan. Okay? So don't try that because it's a waste of energy. So if you look at a profile down through the ocean, so the surface of the ocean up here down to the very bottom, if you plotted a graph of then temperature, you could see that the temperature of the surface ocean is much warmer than the bottom of the ocean, which means that we have this layer of water that's buoyant that isolates the deep ocean from the atmosphere. Okay? It also means that it kind of moves around slightly separately. So the surface ocean is blown around by the wind. Okay? And the details of how that happens is actually not very straightforward, but it broadly follows that kind of pattern, following where the winds blow. But also the deep ocean can circulate as well. But it circulates much, much more sluggishly. Ultimately, it is also driven by the wind, but the details of that are more mathematical than this course merits. So we have, this is a cross-section through the Atlantic. So you can see the surface of the ocean is kind of moving around, blown by the wind. But in the deep ocean, we get water that maybe sinks down in the polar regions, okay, and then starts to basically slowly circulate through the deep oceans, okay, from the high northern latitudes. And we'll go on to how that happens and what effect that has on climate in future lectures. So kind of to summarize the Earth's kind of climate system, it's got lots and lots of different parts. Okay, so it's largely driven by solar radiation coming in from the sun. I guess it's kind of fairly obvious that solar radiation comes from the sun. So that comes down and that hits either something in the atmosphere and maybe radiates back into space, and the amount of reflectivity of the atmosphere might change through time. Likewise, some of that radiation gets to the surface and is reflected off into space, either by kind of changing the albedo, changing the amount of biological cover, that might change the reflectivity as well. But we also have these other things that might affect the climate, so these climate-relevant gases, carbon dioxide, water vapor, and those are affected by a whole bunch of processes. So the amount of carbon dioxide in the atmosphere is potentially dependent on temperature, because of the solubility of carbon dioxide in water. Water vapor itself, water vapor was one of the most powerful greenhouse gases, and the amount of water vapor in the atmosphere is really strongly dependent on temperature. So that's a very strong feedback. So the warmer it gets, the more water vapor is in the atmosphere, which means the more greenhouse effect, which means the warmer it gets, the more water vapor in the atmosphere. So that's kind of an important part of the climate system. The biosphere also heavily impacts the climate system because it's literally made out of carbon dioxide. So if you, for instance, increase the amount of biomass stored in forests, that might reduce the amount of carbon dioxide in the atmosphere and have an impact on climate. It also impacts the geosphere is also important. So the way that the climate system interacts with rocks, okay, either through kind of volcanoes, mid-ocean ridges, or kind of like in island arcs, which give out CO2 or other climate-relevant gases like sulfur dioxide. So those can also affect our simple equation of surface temperature by changing the emissivity of the atmosphere. We'll see tomorrow how weathering has an impact, and do watch that video or video X thingy. That will also impact this system. So there are lots, I mean, the real message of this slide is that there are lots of different interactions within the climate system that affect all of the terms in that wee equation there. Okay? And they kind of are all interrelated to each other. So climate interacts with the biosphere. Biosphere then might interact with the rocks, which might then change the amount of climate-relevant gases, CO2, which then might impact climate again. So it's all kind of horribly interrelated. So different parts of that system react at different rates. So the biosphere might take a couple of years to respond for trees to grow, whereas the solubility of CO2 in water might be potentially more quick. So just as a heads up for what the next couple of lectures is going to go through, we're going to move through the geological time scale from very old to very young, and we're going to look at changes that happen over very long time periods, and as we progress through the lecture series, we're going to look at progressively shorter time scales of climate change and what's driving those. So looking at changes that take maybe hundreds of millions of years and what causes climate to change at that time scale, to kind of time scales that happen on maybe tens to hundreds of years, so over kind of anthropogenic time scales. So to summarize today's lecture, so the greenhouse gas effect regulates Earth temperature, and basically we've derived this equation, and this equation is really important. So we could describe the average temperature of the Earth with this really simple equation, which is only reliant on the power of the sun, or the solar constant, or the amount of sunlight that arrives at Earth, the albedo, so the reflectivity of the planet. If you get more albedo, so you get more shiny, the planet will get cooler, and emissivity. Okay, so the opaqueness of the atmosphere, so how much like a black body is the atmosphere. So the more emissive or more absorptive the atmosphere is, so the more greenhouse gases we have in the atmosphere, the warmer the planet will get. And then there's some other stuff on here which I'll let you kind of like go through in your own thingy. Okay, so I think that's, while I'm here, so this is not, the lecture is over now, so you can start packing up all that kind of stuff. Have you guys been going to these GeoPals sessions? I think they're on every other Tuesday. I'm getting some blank faces coming back at this. So it's run by some of the students in the second, third and fourth year to kind of help you with stuff like this that might, for instance, if you're struggling getting through over how to rearrange all those equations that I've just thrown at you, they might be able to help you with that. So I think it's at 1 till 2 on Tuesdays every other week. So I think the next one is next week after next, maybe? Next week. Okay, so have you been to them? Are they good? Yeah, okay, everyone says yes that's been to them. They're universally loved. There's no bad things about them. So go to those. Do have exit. Do go to the, here we go. Do go to the, go to the, here we go. Go to learn. Join the discussion forum. Okay, so you can kind of like subscribe to it, so every time someone posts you get an email, which can be a bit tedious, so you don't have to do that. But have a look at some of the things on there. Have a look at the video for tomorrow, especially if you don't do chemistry or haven't done chemistry. Okay? Fun times.